can start. Now we have a pleasure to listen to Tom Hartman talk. He will tell us about replica wormholes and the entropy of Hawking radiation. Please, Tom, 45 minutes.
Okay, thank you very much. So I'd like to start by thanking the organizers for hosting this very stimulating online conference. So I'm going to be discussing mostly a paper from November with 4 collaborators listed here. So this is a paper on the same topic that we just heard about, but the goal will be in some context to derive the formula that was discussed. I'll also discuss an upcoming paper with Shigulian and Strominger that will come out any day now. So let me set the stage. There'll be a little bit of overlap with some previous talks, but I'll go through this quickly. So an important part of the information paradox is a large error in the von Neumann entropy of the Hawking radiation. In flat space-time, we imagine collecting the Hawking radiation upon Scri+. We can collect this Hawking radiation as a function of time, so time runs up along Scri+. And then if we calculate the fine-grained von Neumann entropy of the Hawking radiation, then Hawking's calculation tells us that the entropy is thermal. That the radiation is thermal, so this just goes up, up, up until the black hole is fully evaporated. That's a violation of unitarity. And what Page tells us is that when you see enough of the radiation from the black hole, you should start to see this curve go back down, and eventually it should go back to 0 because this is a fine-grained entropy that we're calculating. And the fine-grained entropy in a pure state, if you have access to the full state, has to be 0. By the way, before I go on, let me just say I'm happy to take questions. Please interrupt me right in the middle. I don't have to wait. I don't need to wait till the end. So please jump in. Just unmute yourself and speak up if you have any questions. So Hawking's calculation, of course, is in low energy effective field theory. And I want to comment a little bit on why this is a paradox, or what exactly we mean by paradox. So since we're calculating the effective field theory, this is not exact. And what we really mean by Hawking's calculation is that the density matrix of the radiation is thermal plus corrections. There are 2 kinds of corrections that you can imagine. There are perturbative corrections, which are corrections from gravitons and quantum fields fluctuating on top of this background geometry. And then there are potentially non-perturbative corrections that until recently we really didn't know how to even talk about. Now, in principle, these e to the minus s type corrections, if they exist, could be big enough to fix the problem with the entropy. Because when you calculate the trace, the von Neumann entropy is minus trace of rho log rho. And if you have a non-perturbatively small e to the minus s correction to each element of that density matrix, then you could potentially, well, when we do the trace, we're summing up e to the s terms, and those tiny corrections that looked non-perturbative and exponentially small in the calculation of the density matrix could potentially be big enough to change the entropy by a large amount. They can add up. So in principle, those terms could be enough. But then so what do we mean by paradox? Well, there are various things that people mean by this. Here are 3 of them. So first of all, local or perturbative, the perturbative corrections here, which are the corrections that you get by assuming a local effective field theory on a fixed background or near a fixed background, these perturbative corrections cannot possibly help. So there's a general argument that was laid out by Mator and clarified in the whole firewall paradox story that makes it very clear that it's impossible to correct the density. It's impossible to correct the density matrix enough if all you have are perturbative corrections around the background. So these perturbative terms here are not relevant to fixing the paradox. They're potentially these non-perturbative terms, but that isn't a solution because there's no known mechanism for calculating. There was no known mechanism for calculating these or understanding where they could possibly come from. There was no mechanism for the information to get out. A third part of this paradox, a third reason that this was really considered a paradox is that there are low energy calculations, not just of the density matrix. So when Hawking did the calculation, he phrased it in terms of the density matrix and calculated, effectively calculated this minus trace of rho log rho from his density matrix. But if we want to refine that calculation a little bit and account for these off-diagonal terms, we could do a low energy calculation of the von Neumann entropy itself. And if we calculate directly the von Neumann entropy in the low energy theory and we get the non-unitary answer, well, then we're in a paradox, because then we're doing a low energy calculation, which we think is controlled, and it's giving an answer that contradicts unitary. So there were these low energy calculations of the entropy, not just of the matrix elements. And that's the calculation that I'm going to revisit in this talk and describe this contribution from replica wormholes that at least in some cases, and I think likely more generally, modifies these low energy calculations when you include replica wormholes.
Tom, can I ask a naive question?
Sure.
If I phrase a burning piece of coal in this language, would you say that the perturbative corrections unitarize this thing, or what's the statement for a burning piece of coal in this language?
I'm not sure that there's a clear separation between perturbative and non-perturbative. It certainly could be the perturbative. It could be what I'm calling perturbative here, because the argument that for black holes tells you perturbative corrections can never help is an argument that relies on a smooth horizon. So I don't see any reason the analog of the perturbative corrections couldn't fix the problem with coal.
I see. Thank you.
Okay. So the goal of this talk is to show that a direct calculation of the von Neumann entropy in the low energy effective field theory using the replica method actually gives the unitary page curve. I won't show this in general, but in certain cases. So the unitary curve, the conclusion is that the unitary curve is a non-perturbative effect from complex saddles in the gravitational path integral that we call replica wormholes. This is a semi-classical gravity calculation. It doesn't use holography. It reproduces the holographic results of previous papers that have studied this island rule and the role of quantum extremal surfaces in this very interesting recent development. The derivation that I'll describe has been completely done only in ADS2. However, I think that this mechanism probably works in general. Certainly it hasn't been shown. There are some hard calculations that need to be done to show this completely, but my bias at least is that the island mechanism and the replica wormholes behind it both carry over to the more general case. So let me quickly review the proposal of these two papers from last year, which we've heard about in other talks in this conference. I'm going to phrase this in flat space, although that won't be the model that I'm studying exactly, but let me just phrase it first very generally. So I've drawn here the Penrose diagram for an evaporating black hole. I've split it into various regions. There's an imaginary line out here, which is roughly you should think of this line as being a few short-shielded radii outside the black hole. So inside that line, gravity is important and gravitational effects can be large. Outside that line, I'm going to assume that we can basically treat gravity as weak and treat it like a quantum field theory. So effectively, gravity is turned off outside the line. And there are some simple models in ADS2 where this is realized explicitly. At least it's possible to do in the low energy theory, the effective field theory that we'll be using. So the conjecture of these that came out of these papers is that when you calculate the entropy of region A, that is the entropy of the quantum fields, the von Neumann entropy of the quantum fields on some region outside the gravitating space-time, then it's given by this formula, the quantum extremal surface formula, or the island formula, or the quantum Ru-Takanagi formula. I'm not sure exactly what to call it now, but the point is that what this proposal says is that at late times, there's an additional region inside the black hole, the island region, and the island region, after the page time, is effectively encoded in the Hawking radiation. The island region is determined by extremizing the generalized entropy in this equation above. So this proposal was initially based on holographic calculations, but part of the point of this talk is that this does not require holography. It looks like a holographic formula because it looks like the Ru-Takanagi formula, or the quantum corrected Ru-Takanagi formula of Engelhardt and Wall. However, that's just a historical accident, I would say, or maybe not an accident, but it's historically came from a holographic point of view, but I think does not require holography and really is more general than holography in ADS-CFT. Before so our goal will be to derive this formula from the gravitational path integral in some setting. Before I do that, I just want to make a few remarks about the interpretation and the structure of the quantum state that this suggests. So I think there's a nice toy model for the quantum state in the language of tensor networks. I want to describe this briefly. So a tensor network is a representation of a quantum state using a bunch of tensors. The quantum state that I've drawn here is a simple toy model that seems to capture the late time structure of the quantum state on the Cauchy slice IGBA. So the tensor network, so this tensor network, each of these boxes is a tensor. Each of the bonds connecting the boxes is a contracted index between the tensors. And the free indices on the tensor network represent the Hilbert space of the state that you're talking about. So I've drawn this tensor so the tensor here you should think of as living in the Hilbert space associated to B and A. And there are no external legs on the gravitational regions because it's gravitational, and it's encoded holographically in the outside. When I say holographically, I'm just using this as a toy model. I'm not really using ADS-CFT, but I think this is the way to think about this quantum state. So in a tensor network, so let me explain a little bit what these lines are. So excuse me. So I have to figure out how to go back. Okay, so the lines between the boxes are geometric entanglement, and so these encode the entanglement that you get these encode the area contribution to entanglement. these long lines connecting region I to region A, these represent the Hawking radiation. So at late times, we have a lot of entangled Hawking pairs, which have one pair near scri plus in region A that's entangled with its interior partner in region I. So this encodes the structure of entanglement in the quantum state. And for generic tensors, a very intriguing thing about tensor networks is that the von Neumann entropy is proportional to the number of cuts that we need to make to separate A from the rest of the network. This is an observation of Brian Swingle. It was a starting point for a very interesting correspondence between tensor networks and geometry. The reason for this is simple. It's just because these are tensors with a bunch of indices, and if you want to encode more entropy if you want to have more entropy in a quantum state, then you need to entangle your region with more degrees of freedom. On this picture, that's represented as having more lines to cut because there are more indices, and you can therefore encode more entanglement.
Sorry, question, Tom?
Yeah.
Hey, so could you say again how you're defining the split between G and B? Is it supposed to be sharp or?
No, so this is just supposed to be a toy model. This is not supposed to be anything like an exact description of the quantum state. In actual gravity, I don't know how to split G and B, but what I'm drawing here is just a tensor which qualitatively captures the same features that seem to make sense in the geometric case. I'll not answer that question because it's just supposed to be a toy and we don't really know how to do that splitting. In ADS, we do have a pretty good idea how to do that splitting because in that context, the splitting between G and B will occur at the ADS boundary. And right. The exterior region will be this flat space that's glued on the outside.
But is it clear that that splitting can happen in flat space, or will you argue that there's a way to make sense of it in flat space?
No, I won't. No, I won't.
Oh, okay.
So that I think is an important question. We don't know how to do that.
Okay, thanks.
Yeah. Okay, so at early.
Another question.
Yeah.
If there is a lot of entanglement between I and the island and A, shouldn't we expect that there is a Einstein-Rosen bridge between the two?
Well, if you mean a sort of an ER equals EPR type bridge, then I think, yes, I think that's one way to think about this. You can, so these lines up here represent the entanglement between I and A. And these lines are sort of the wormhole of ER equals EPR. Now, it's not an Einstein-Rosen bridge in the geometric sense. It's just a bunch of lines in the tensor network. It's not geometrical.
Yeah, but yeah, that's the question. Why we don't see it in the geometry?
Well, I don't think there's any reason that we'd expect to see that in the geometry. This is just a black hole geometry. So I don't think there's any, there's no additional bridge there.
I mean, it seems to go contrary to the ER equal EPR then, no?
The ER equals EPR proposal, in some contexts, is a geometric proposal for an Einstein-Rosen bridge, but in the context of an evaporating black hole, it's not geometric. It's really, I think what they were proposing was that there's some quantum version of a wormhole, whatever that may mean in quantum gravity, some quantum version of a wormhole that appears connecting I and A. And this is, that's in this toy model represented by the matter entanglement. But I don't think that it doesn't need to be geometric in general.
Okay, thanks.
Okay, so I was saying that the entropy is given by the minimal cut. Now, at early times, the entropy in the Hawking radiation will be small, and the easiest way to remove region A from this diagram is to cut along the red line that I've drawn. However, the number of lines, so these lines on the top that represent the matter entanglement, the number of pairs is increasing as the black hole evaporates. So the amount of entanglement, the number of lines there, is growing with time. Meanwhile, this cut over here represents the area of, essentially the area of the horizon, the geometric entanglement at the edge of region A, and that is shrinking with time. So eventually, it becomes more economical to cut the diagram this way. So in this simple toy model, Tensor Network, we see something that looks very much like the island phenomenon. And at least at an intuitive level, this is just supposed to be a rough qualitative picture, but at an intuitive level, this picture illustrates what it means for region I to be encoded in the density matrix of region A, to be encoded in the Hawking radiation. We can think of it as this additional tensor that's part of the definition of the quantum state. The transition from the early time cut to the late time cut is the page transition. It occurs at the page time, and this indicates the formation of the island region I, which now can be accessed through the radiation. A fact about these tensors is that operators in I can also be pushed through the tensor network to be rewritten as operators on A. That's another way of saying what it means to be encoded in the radiation. That the algebra, for example, some simple field operator in the interior region I can be rewritten in principle by some complicated operation in region A. The other thing that this picture suggests is that this is a version of holographic duality at Scry Plus in flat space. And I think that's very intriguing. I don't have much more to say about it, but it's a holographic duality at Scry Plus in sort of the same sense of entanglement wedge reconstruction in ADS-CFT. It's not necessarily a duality between quantum theories like we have in ADS-CFT, but rather a duality between quantum states, that we have a geometry in the bulk that represents a quantum state on the non-gravitational degrees of freedom in region A. Okay, so that was just sort of an aside on how to think, on how one way to think about what it means to have an island. And now I'm going to turn to the derivation of this formula. I'm going to study a particular version of the information paradox, which makes it easier to do the calculations and draw the pictures. This is a version for eternal black holes in ADS-2. So I'm drawing the model here. This is an eternal black hole. The strip region that's shaded, this is the gravitational region in ADS. This is a black hole in ADS-2. And it's being glued to Minkowski space on both sides. Gravity is just in the shaded region. And I'll try to stick to that convention throughout the talk, that shaded regions have gravity, white regions do not. So there's a two-dimensional conformal field theory here, which is everywhere in the diagram, and JT gravity in the middle. I'll assume that the conformal field theory is a large N field theory. It does not need to be holographic. It just needs to be large N so that we can control the quantum fluctuations. It could just be N free fields. So this eternal information paradox, which we heard a bit about in the previous talk, is as follows. We take region A to have a component on each side of the eternal black hole. Then we evolve both sides of the, then we evolve in time, moving both sides upward on both sides of the Penrose diagram. As we do that, the entropy of region A increases linearly because, well, one way, I think the easiest way to think about this is to think about the complement region. The complement region, which has the same entanglement entropy, the complement region is the growing interior of the black hole. So that is getting longer and longer, and we're depositing these interior partners of Hawking radiation into that longer and longer wormhole. So as entropy is increasing linearly. And in this situation, an island appears at late times, according to this island rule, where you take the generalized entropy and you extremize over the choice of island, and the island dominates over Hawking calculation and saves the page curve for you. So this replaces the linearly growing page curve by one that grows and then saturates. So what I want to describe is how this can be reproduced directly from the replica trick in the gravitational path interval. The basic idea in sort of a cartoon version is the following. We're going to do the replica, when we do the replica trick to calculate the entropy, we have to consider multiple copies of the black hole. So here's a case with three different, so we started with this eternal black hole, and when we do the replica trick with multiple copies, so here's a case with 3 black holes. And the basic idea will be that in this replica method, where you have to consider multiple black holes, dynamical wormholes can appear connecting the black hole interiors. These are saddles of the gravitational plus matter path integral, but they're complex saddles that are hard to construct because they don't really have symmetries. We can, in some simple cases, we can construct them by explicit solution of the equation motion for gravity plus matter, including the one loop corrections of the matter. In the replica limit, which gives the von Neumann entropy, these saddles disappear. So when you just have one copy of the system, so there are these wormholes when you have multiple copies of the system. The wormholes disappear when you go down to just one copy of the system. There's no wormhole anymore. However, the saddles for the saddles for the replica situation can leave an imprint on certain observables, and that imprint can be large. So actually, although the wormholes go away, they leave a large effect on the density matrix that can be seen by looking at the von Neumann entropy. That'll be the basic idea. Now I'm going to go through in a bit more detail how these replica geometries, how these wormhole geometries appear. So we're going to do a replica calculation where instead of calculating trace of rho log rho, we calculate the replica partition function trace of rho to the n. This is just a trick to deal with the log. So we're calculating trace of rho to the n, and then in principle we can extract the von Neumann entropy by analytic continuation in n and taking the derivative near n equals 1. Let's start with the simplest case, n equals 1. So I want to explain this picture. This is trace of rho, and this picture is just the standard Euclidean black hole. So so Euclidean time goes around the circle, and this is the Euclidean version of this ADS2 black hole glued to flat space. So the Euclidean black hole in this gluing situation, flat space is the region outside the circle, and gravity, the JT gravity coupled to the matter field, is the region inside the circle. So when we do the Euclidean path integral, what we're supposed to do to calculate trace of rho is just the usual Euclidean saddle for the black hole. We impose some boundary condition. It's important that we don't fix the geometry by hand when we do this calculation. What we do is we fix a boundary condition. That's what this dotted line. So we fix a boundary condition on this dotted line, and then we're supposed to solve that boundary condition is the Euclidean periodicity condition that fixes the temperature, and then we're supposed to solve the gravitational plus matter equations of motion subject to that boundary condition. Of course, when we do that, what we get is just the Euclidean black hole. So now, now what I'm drawing is the solution, the saddle that contributes to trace of rho. It takes this boundary condition, which was this disk boundary condition with a specified temperature, and it fills it in with two-dimensional hyperbolic space, which is the Euclidean black hole for ADS2. So now that we've filled it in, we have a saddle, and what we're supposed to do is calculate the action of the saddle, which of course is the free energy of the black hole, and that is how we would do the n=1 replica calculation. Let me pause here for questions to see if this diagram was clear, because now we're going to go to the more complicated case. Are there any questions?
I have a quick question. Tom?
Yeah, sure.
So this is you're doing in the context of an eternal black hole only? Oh.
Yeah, at this point, this is the eternal black hole in ADS2 glued to flat space.
The reason I was asking is that if you were starting not with the eternal black hole, the island would, that island point would be inside the horizon, which is sort of lost in the Euclidean continuation.
Yes, that's right. So that can even happen depending on parameters. That can also happen in the in the eternal black hole, that there may not be an island at time 0. What I'm really imagining here is doing this calculation in Euclidean and then analytically continuing to real time. So it makes it easier to draw the pictures in Euclidean, but the saddles that will actually be responsible for the interesting islands will be complex saddles.
Oh, I see. Okay.
Move things into Lorentzian.
Okay, I understand.
Okay, any other questions about this picture? So now I'm going to go to n=2. And this is where things get interesting. So now we imagine we're calculating trace of rho a squared. What I've drawn here is the path integral, is the Euclidean path integral that calculates trace of rho a squared. The cuts, so the circles are the gravitational region. On the circles, we impose a boundary condition corresponding to the correct temperature. These cuts in the exterior region, these are region A. So we have 2 copies of the system. Each of those is associated to a factor of rho A. And the matrix so now we have this operator rho A. The matrix multiplication that defines the trace corresponds to a gluing of the manifolds along region A. So that's what these bridges denote. What the bridge means is that if we're on the top copy, moving along and we hit the cut at region A, then we come out along the bottom. So these bridges join them together, and similarly, if we go through the other one, we come out the bottom over here. What I've drawn so far are the boundary conditions for the path integral that calculates trace rho a squared. We don't get to pick the geometry. We only get to pick the geometry. We only get to pick the boundary conditions, and then it's up to the gravitational path integral to fill in, to find a saddle that solves the equation of motion. So when we calculate the path integral with this geometry, there's one obvious contribution, which is just 2 copies of the Euclidean black hole glued together along region A. That's the one I've drawn here. And this I call the Hawking saddle, because this is the calculation that would give the standard Hawking answer for, Hawking style answer for the von Neumann entropy of region A. Each of these disks is just a copy of the Euclidean black hole. And if we're to do the replica trick this way, then we're just going to find the answer that corresponds to doing quantum field theory in curved space, which is the standard Hawking style calculation of the entropy. However, now that I've drawn it this way, it's clear that there's another potential contribution that we should think about. Remember that we don't get to pick the geometry, we just get to pick the boundary conditions. In this case, we had a boundary condition that consisted of 2 circles with the thermal periodicity. There's another topology that can contribute here, which I've drawn on the right, that connects the two copies in the replica trick. So this is the replica wormhole. If we think about the calculation of the action for trace of rho A squared, then it's a sum over saddles. Well, we can approximate it as a sum over saddles of e to the minus s. The first contribution here comes from the Hawking saddle, but if there are these other saddles, and we have to, that's something that we have to check, we have to look for saddle points, but if there are these other saddles with other topologies, which there will be, then they can give additional contributions to the path integral. And in this case, the exponents that are showing up here are the second Renyi entropies. So by definition, the thing that shows up up in trace rho squared gives you the second Renyi. So that's why I've called that S2. So let's think about how big these terms are. Because when we have multiple saddles, we have to pick the dominant one. The first term is suppressed by large entanglement of the radiation with the interior, because this is just the second Renyi of the Hawking calculation, Hawking style calculation, and therefore when the Hawking entropy becomes large, the entanglement is large, and the second Renyi will also be large. So in a situation that's like a late time black hole where you get into problems with the information paradox, in that kind of situation, that's exactly when you expect saddles like this to be highly suppressed. The other term, the one coming from the wormhole, is also suppressed. However, it's only suppressed by the topology. So in JT gravity, there's a contribution to the action, which is the Euler number, and that gives you a suppression of higher topology contributions. However, that's just a constant. So the replica wormhole contribution has a constant suppression, and the Hawking contribution has a suppression that it becomes even more suppressed with time. So eventually, when the entanglement between the interior and the radiation is large enough, we can expect an exchange of dominance between these two saddles, and that'll be responsible for the page transition. In the replica trick, we should consider all n. So let me talk about the higher replicas. We'll assume that the replicas have a Zn symmetry, a cyclic symmetry that rotates among the replicas. So what I've drawn here is a case with n equals 3. This is a n equals 3 replica wormhole joining 3 copies of the original system.
Sorry, I have a question.
Yeah.
Are these not actually true saddle points of JT gravity?
These are actually true saddle points of JT gravity coupled to matter.
So the matter fixes something, because in pure JT gravity, it is known that there are wormhole-like geometries, but they are not actual saddle points. So
yes, good, good. Yes, the matter is essential here. So the fact that these cuts, the matter cuts, are glued together, essentially gives you a Casimir energy type contribution from the matter that supports the saddle point, that supports the gravitational saddle. So the contributions of matter are very important.
Okay, thank you.
When there's this cyclic symmetry, we can take a quotient. So that's what I've done on the right. And we can think of this as being the appearance of a new branch cut inside the interior of the Euclidean black hole. So the picture on the right is just supposed to capture the topology of the picture on the left. Each of these new branch points is a threefold branch point. This has the same topology as the picture on the left. You can convince yourself that it has the same topology by staring at it for a little bit. It has the same topology, but it's important, I do not want to put singularities in the gravitational region. So although I've drawn these branch points, they're actually perfectly smooth points on the replica geometry, because we're supposed to solve the gravitational equation. And if I were to put a conical defect, that would not solve the equations of motion. So the metric, in other words, when we look at the quotient manifold, the metric near those branch points adjusts itself to make sure that the geometry is smooth in the picture on the left. So these branch points are just supposed to capture the topology. The conclusion is that these twist operators can appear dynamically in the gravity region, these branch point twists, W1 and W2. Now, including these saddles in the replica calculation gives the island rule for the entropy. I'll sketch this briefly. This closely follows an argument that was used to derive the Ryu-Takanagi formula by Lefkowitz and Malasena, Dong Lefkowitz and Rangamani, and Dong and Lefkowitz in a series of papers. So here I'm just going to sketch it. The basic idea is that when you, and I should say that now that to get the entanglement entropy, we have to go near n = 1, and it's hard to picture what these wormholes look like when n is not an integer. So we started with these wormhole geometries. However, once we go to the quotient, it's perfectly sensible to analytically continue in n. Okay, so so that's how the analytic continuation is done. We first construct the higher n wormholes, then we go to the quotient, and then we can continue in n. The equations of motion just fix an n-dependent boundary condition on the metric near the branch points. So now that we can analytically continue in n, let's look at the action. When we calculate trace of rho a to the n, there's a gravitational, so this is going to be a bit schematic, but there's a gravitational part coming from JT gravity, which has a dilaton and a metric, and then there's a matter part coming from the CFT on a non-trivial manifold. We're going to take this effective action and we're going to find the effective action near n = 1. Well, the contribution of the matter fields to the effective action is determined by the matter entanglement entropy. So the thing up in the exponent here is the entanglement entropy of the matter fields. The reason for that is that if we're doing quantum field theory on this defect geometry, that's exactly the same calculation we would do to calculate entanglement in quantum field theory. However, it's not the entanglement of region A. It's the entanglement of the full region that you get by taking the union of A and this new branch cut, region I. Okay, so that's the matter term. There's a contribution from gravity, which is given by the area. And therefore, the effective action is just the generalized entropy, which is the sum of the area and the quantum field theory term. There are also some moduli here, which correspond to the location of the twist points. So what I've written is an effective action for those for the dynamical twist operators. The conclusion is that the effective action of the defects is the generalized entropy. Now, when we find the equation of motion for the moduli, that equation is the island rule. And when we take n to 1 and calculate the entropy from this replica calculation, we get the extremum of the generalized entropy. So this is the island rule, and this gives the unitary page curve for the eternal or the evaporating black hole. Okay, a couple comments. Note that we're calculating the entropy of region A, and this is the entropy of a quantum field theory density matrix. Now, in region A, there is no gravity. There's just quantum field theory. The island appears in that formula, but ultimately it's in the Hilbert space of the matter fields. I think a nice way of thinking about this is that we inserted these defect operators at the edge of region A, and what we found is that these new dynamical defects can be pair produced inside the black hole interior, or near the black hole horizon in this case. So the cost of, so we have these new dynamical defects. The cost of pair producing these defects goes as area, but eventually that cost is overcome by the growing Hawking entropy. So let me skip the explicit solution of the replica equations. There's a explicit, we can find in great detail these replica solutions in certain cases, and they have the action that I just described. But I'm running low on time, so let me just make a few comments about the flat case and then conclude. So in flat space time, as we just heard in the previous talk, the CGHS or RST models are theories of two-dimensional dilaton gravity that have asymptotically flat black hole solutions, and we can ask whether a similar analysis applies here. These models exhibit the same island phenomena as black holes and anti-de Sitter, and the islands, if you use the island rule for the entropy, give you a unitary page curve. There were these two very nice papers earlier this month about this. We just heard about one of them, and we have another paper on this coming out soon, which was partially scooped. One notable difference, if you saw the previous talk, is that we used free matter fields as opposed to strongly coupled holographic matter fields, but that essentially doesn't change the position of the island or the conclusions. Now, it was shown in the 90s that black holes in the RST model lose information, so what's going on? Well, the RST model, as originally defined, has fixed topology. You can think of it as a conformal field theory on a fixed topology. So the replica wormholes were not included by definition in the original RST model. I think it's likely, although not proven at this point, that including replica wormholes in the Euclidean path integral gives a principled derivation of the island rule for RST, just as it did in ADS2 with JT gravity. We've showed that the replica equation of motion via the defect in the RST model can be solved and give you exactly this extremization condition for the generalized entropy. So this gives a local solution for the replica wormhole in the RST model. However, the global solutions haven't been constructed. So let me conclude there. I'm out of time, but I'll just end with these questions. Some questions are, what about small n? We used large n matter fields to control the quantum fluctuations. I think that the same analysis carries over to small n, but requires more care with dealing with these saddle points. Another open question is, what about the Lorentzian interpretation? This is a Euclidean calculation. In that sense, it's like the Euclidean calculation of the black hole entropy from the on-shell action. And it does not directly tell you about how the information actually gets from the black hole interior out into the radiation, what the actual evolution is that defines the quantum state. And finally, I think, as I was describing with the tensor network, this really suggests a holographic encoding of the interior on Scri+. But this is something that we need to understand better. And I'll stop there. Thank you very much.
Thank you very much for your very instructive talk. Any questions, please?
You mentioned at some point the appearance of second Rényi entropy. Does your result imply that for this entropy and other power-like entropies, there is also no information paradox?
Yes, I think so. Yeah, yeah. So the saddles that we're constructing are directly calculating those higher Rennies, and they prevent them from growing at late times. The wormhole saddles have give a constant contribution, which will eventually dominate.
So all of these entropies does not have information paradox, and actually, and and limit also does not have. This is the situation, right?
That's right.
Yeah. Thanks.
More questions, please?
Well, maybe I have a question. Is it right that the origin of the island in this picture is actually the result of the Quotian procedure that you described?
Sorry, I couldn't quite hear. Can you repeat the question?
Is it right that the origin of the island in this picture is the result of the Quotian procedure that you are suggesting? Simply, the question is how this additional branching points arise and the cut between them as a result of this quotient process.
Are you asking if the quotient was essential?
Yeah.
I see. Well, the quotient was not essential. It was essential for us to assume a replica symmetry. That is a ZN symmetry that, well, no, let me take that back. I think the quotient was important because the quotient is what allows us to analytically continue in N. So I think that the quotient is not really an assumption, though. The assumption really is that there's a ZN replica symmetry, the cyclic symmetry permuting the replicas. Once you have that symmetry, the quotient is just a trick for how to think about those ZN symmetric saddles. Is that a question?
What is the compulsion actually to get this extra cut that joins this W1 and W2 points in your picture?
Yeah, the extra cut is accounting for the topology of the replica wormhole. It's not a, it's, let me go back to that slide. So it's,
so maybe you can show this
the same manifold.
W1 and W2 on the left side of your graph.
Yeah, so this, there's a fixed point of the Zn, there's this fixed point of the Z3, which are these two red dots on the picture here. And that fixed point of the Z3 looks singular on the quotient, but it's regular on the full manifold.
Ah, that's in this sense, the regularity of these points. Yeah, I see. Mm-hmm. But this cut between these 2 points, is it actually one of the 3 ones on the left side?
The cut on the left side is represented by these by the red curves. So there's the cut collapses into the red curves. When you take this Z3 quotient, collapses into this one cut. Because if you go through the cut, that takes you from one copy to another. So we can, if you look at the full manifold, then you can imagine going through the wormhole and coming out the other side, and you have to go through the red line to do that. And that corresponds on the quotient picture to going through the cut and landing on the next copy.
I see. Okay, thank you.
Okay. More questions, please?
Yeah, hi, Tom. I have a question regarding your tensor network picture. Yeah, can you go to that slide if you can? Yeah, I want to understand a little bit better your argument saying I should be the island, say corresponding, say I should correspond to the say entanglement wedge for A. Because naively what this picture suggests is just I is entangled with A rather than say I is the entanglement wedge of A.
Yeah, but the point is that if we're, so say we want to use this tensor network to calculate the entropy of region A. Mm-hmm. And we should cut A from the network. And we should do it in the most economical way, which involves the least number of cuts.
Yeah.
And the point is that at late times, that was this cut here, so that we don't cut off I. And when you think about the way that say a Renyi calculation works, or if you define operators on region I, what this means is that you sort of still have access to the operators on I directly from A. So that's how it's analogous to the entanglement wedge.
Yeah, but I want to make a distinction between, say if we have say if we have external black hole in ADS, and then say the left CFT is entangled with the right CFT, but the left CFT is not the entanglement wedge of the right CFT. That's a completely different concept.
That's true, but in that case, the left CFT has its own legs. You know, if region I were the left CFT and they were highly entangled, then it would have its own Hilbert space there, and the entanglement cut that I just drew would not be allowed. So I think it's important that region I is a gravitational region, and we shouldn't give it its own legs.
Somehow I want to understand this distinction. Somehow that here you have somehow. Also normally when we say just again in the just ordinary CFT case, ADS case, when we say a region is the entanglement wedge, say of it's some boundary sub-region, we don't say that region is actually entangled with that boundary sub-region, right? They're just equivalent.
That's right. This is a little different because what I'm drawing here is I have not drawn the transverse direction. I have not drawn so when we think about the entanglement wedge in ADS CFT, we usually just draw the transverse direction. Mm-hmm. But this is more like the picture for ADS2, or if we suppress the extra directions.
Mm-hmm. Yeah, understand your picture. I think your picture is what we normally think from
maybe I'll draw the picture for vacuum. Maybe it'd be helpful if I draw the picture for vacuum. For ADS2 alone, I would draw it like this. I would draw a boundary, which you can think of as the SRK model, or you can think of this as the holographic representation of ADS2, and then there would be a gravitational region here. So this is the corresponding toy model of the ADS2 vacuum. And if we ask what is the entanglement wedge of region B, well, it's just everything.
Mm-hmm. Mm-hmm. Yeah. I think I understand your picture. Somehow I just did not somehow somehow this is still one need to do a little bit leap somehow from this tensor network picture somehow to argue. Yeah, I just want to know whether there is a leap that you argue from the tensor network picture somehow I is the entanglement A, or you think that just follows from the standard rule.
I think it requires special properties of the tensors. But what I'm saying is really just that this is how the tensors should work if we want it to be similar to the quantum state we get in the bulk. But it does require some special properties of the tensors. This won't be true for any old tensor network that I draw.
Okay, thanks. Yeah.
Please, more questions?
So there was a question in chat from Panos Bedzios about, so the question is the following: how do we know that the replica symmetry is not broken and that the continuation is well defined? Is it a postulate or shown?
It's a postulate. The assumption is replica symmetry is an assumption. I think that since we found saddles, it's a self-consistent assumption. If we wanted to, so I think it's important here that we took large N in the matter sector so that we could ignore the fluctuating gravitons, and that to properly incorporate the entanglement entropy of the gravitons in this story, we may have to address the differences on different replicas. But it's really an assumption. The same assumption was made in the derivation of the Ru-Takanagi formula, but I don't think there's any known justification in general.
Thank you.
Please, any question? Okay. If there is no more questions, let's thank Tom once again. Okay, thank you very much.